Resistance is not futile. Welcome back to Mike's Radio Repair and Restoration. Today we're going to take a little bit of an in-depth look at resistors. In many of my videos we've talked about resistors. We've talked about tolerances, and we've talked about when to change them. We've talked about where the ones are that are likely needing change. But I find that a lot of people skip over. They watch parts of my videos and not full, and they're not necessarily getting all of the bits and pieces that I'm communicating. I'm going to try to pack it all into this video. So there's going to be stuff you've heard before, but insofar as resistors, there's a fact or two that you really need to know, and you really got to stay tuned in on this one. It's rather important that you pick up some of these facts, especially one in particular in regards to carbon resistors. So we're going to go through all of that. We're going to look at the old style resistors. We're going to look at the new style resistors, how they're made, and where they will be used, and we'll look in different schematic diagrams to point out different areas where certain resistors would likely be used and where certain resistors absolutely have to be used. So lots of good information, probably some you've seen before, probably some you're aware of, and maybe some new bits and pieces for sure. If you're a new guy starting out, there's very important information in this video that you probably don't really want to skip over. So with that, let's take a look at the old familiar ones we're looking at. We're going to start with carbon resistors. Okay, here we see a selection of resistors in front of us here. We're going to stay right at the start here now with these fellas here. These are carbon resistors. These are what you usually see in our old receivers. Of course, when you get into the older broadcast band, 1920s, 1930s receivers, you see a lot of dog bone style resistors too. These are considered carbon resistors. Again, quite common to come across. They definitely fail, certainly when they're under heavy load. In previous videos, we've talked about where they fail, although they can fail anywhere. They tend to drift considerably when they're setting bias on a tube of, an anode or a cathode resistor, and we'll look at a schematic and see where that might be. We're also going to look at how they're constructed and special properties about them, because between the carbons and the newer ones, there's a construction difference that's really important we're going to get into. But we can see here now, these are the typical half watts, these smaller guys here. This guy here is a 1 watt. This is also a 1 watt, and these three bigger guys here are a 2 watt resistor. And I generally replace half watts with 1 watts, and just so that you can see the size difference here now. This is a modern metal film. We'll get into that in a bit. 1 watt resistor. So as you can see, the size is similar. So if I can replace a half watt with a 1 watt, why would you not? Your radio is going to last longer and stay on spec a little bit longer. Next is considering the resistor. A lot of these are rated at 10% tolerance. That means if you have a 1000 ohm resistor and it drifts up to 1100 or down to 900, you replace it. The resistors that I use are 1%. They're much tighter in tolerance. They work much better. I've always kind of stuck with that. I was very good friends for a long period of time with a gentleman who's now sadly passed away, who was an engineer for the Hammond Transformer Company, and he did a lot of designing of things. And he was very adamant that when he designed a circuit, if he designed a 10K resistor in this place, then that is the resistor that you use, not a 9.9. He was very adamant. He says, There were places where certainly, a little bit of leeway was okay in a given circuit. In some circuits, it wasn't. He says so. He was very adamant about resistor accuracy in what he designed. So that kind of sort of stuck with me, and I've always tried to use 1% wherever possible. In some cases, when you get up to in these standard resistors up around 10 or 20 megohms, which is a pretty large amount of resistance, sometimes you can only get a 2% resistor, and that's fine. But it's certainly better than a 10. So I generally don't use 10 unless I'm into a power resistor, where we'll get into a little bit later. But let's take a look and see how these guys are built, which is kind of interesting. Okay, here's our standard old-fashioned resistor we're all used to. And the core is probably as you imagined, a carbon composition material, and the leads are embedded into it, and it's set at a given conductance by the manufacturer, of course encased in the, the brown material that we see. And of course, it has all the identification bands on it. I've placed a link to a nice resistor calculator that's online that the new folks can use to learn to read these off quickly by eye. And the last band, of course, is the tolerance band. This one here shown as silver, which is a 10% tolerance, and gold is 1% tolerance. So no surprises here. It's the next area here where there's a little bit of a surprise. So here we go, and this is kind of sort of microscopically looking at the carbon grains of the composite carbon material in the resistor, and a little bit of capacitance actually sets up between the grains. Not a lot, not so much that it usually affects anything. It doesn't usually affect anything at all, but nevertheless, it's an interesting fact that it's there. There's a property in the newer metal films that we absolutely have to be aware of that we're going to get into next, but that's kind of sort of the plain paper bag carbon resistors, plain vanilla, I guess is how you would say it. How they're put together, but they're pretty straightforward. Okay, moving on to more modern resistors. These are known as metal film resistors. They are built quite differently, and that's important for us to understand because there are places where you can and cannot use these resistors that we're going to get into in this video. So as long as you keep that top of mind, everything will be well. But just for comparison's sake, up here we've got a brown metal film, and it's a half watt, and there's an old-fashioned half watt, and we've got a 1 watt here compared to a modern day metal film 1 watt, and here's a 2 watt compared to a modern day 2 watt. You can see there's quite a size difference. So these resistors are perfectly fine for use with the proviso you understand how and where you can use them. And the difference lies in the construction, and we're going to get into that and understand why that is in the next couple of slides we're going to look at. Here is a look inside a metal film resistor. And they use a carbonized metal film that's applied on top of a ceramic carrier, and there are spiral or helical grooves cut in it to create the resistance path. So if you make those cuts smaller, of course you've got a longer helicoil, so you're going to get more resistance. It's kind of an ingenious way of dealing or making a modern resistor. I thought it was kind of sort of cool. And we can see the difference here between a lower resistor and a high resistor. The cuts are there is more of a spiral, so the resistance would go up. And you might ask, well, why does that affect where I place a given resistor? Well, in the carbon resistor, we learned that there's a small amount of capacitance, which generally doesn't affect an RF circuit. But this is a spiral or helical cut, or you even want to go so far as to call it a coil. When you have a coil, you're going to induce what's called inductance. And that can really screw up an RF circuit. It can add inductance, and it can really muck things up. So you really can't use a metal film resistor like this in an RF circuit. And we're going to get into a schematic and identify, you're going to learn to identify where these resistors are that you can't use metal film resistors with. And you might ask, okay, well, if I have a resistor that has RF flowing through it, what do I replace it with? The old carbon resistors aren't made anymore, and new old stock is drying up. I'm sure there's some out there, but there's not a lot. The modern equivalent to use are what are called OY or OX class resistors. They are directly um, to replace carbon composite resistors, and this is what you have to order or use when you are using or replacing a resistor to which RF flows through. And again, we will go and we'll hit the schematic at the end of this video, and we'll do some learning about where these resistors might be. Okay, the last class of resistors we're going to look at today are what are known as wire wound. And all of these you're looking at are wire wound. They're usually a much higher wattage resistor, like beyond 3 watts, 5, 10, 15, 20 more higher wattage. They are not used to pass RF. They are normally used in power supplies as part of a filtering circuit. A voltage dropping ordeal to a voltage regulator tube, and they usually run quite hot. The one on the top here is a modern wire wound resistor. They're okay. They'll do the job. Myself, I prefer these older guys. They are the ceramic wire wounds, and sometimes you can snap them up on eBay as a good deal. And here's a more modern, smaller wire wound that's a 5-watt resistor. But the older guys tend to last longer than these fellas. Now, these are commonly found in power supplies. They commonly work very, very hard. They also get very, very hot, and they drift. You may also find this type of a wire wound in an old radio, a dog bone style, that they most certainly drift in a power supply. Then they get very hot. They get hot enough during operation, they will burn you if you accidentally touch one. So they work hard, they drift, they need to be checked. The better quality ones like this will last longer. Like these old ohmites, they don't, sometimes they go, but a lot of times they don't. But these will drift, and these certainly do drift. So they need to be checked. There's nothing special about them. And we'll look at a quick slide to see how they're built, and there'll be no surprises here. So let's take a look at that slide now. Okay, this is the basics of a wire wound. It's a resistance wire wound on a ceramic rod in order to obtain the given resistance that you might be after. Nothing special here, but again, you can see it's wire wound, so it would be inductive. It would not be used or suitable for use in an RF circuit. And again, they're pretty basic. No surprises here. I don't think we need to explain much more about these. So let's apply what we learned to a schematic here so that you understand all of the concepts that were presented here today. So the first thing we want to look at are resistors that set the bias of a given tube. And they're the ones that tend to work hard with the standard carbon type resistors. And you'll often find them attached to either anodes or cathodes of tubes. Let's find an example here, V4. This schematic we're looking at, by the way, is from our Heathkit DX60 transmitter project that we did. Here is a 33K 2-watt resistor. I'm sorry, my pointer's not very clear, but R26 here is denoted as 33K 2 watts. It's quite apt to drift. As is the 1 mega on the plate here, and you've got another plate resistor here of 470K. These ones are quite apt to drift. You've got another one here. That's 1,000 watts or 1,000 ohms at 1 watt. That would be apt to drift. So let's deal with wire wound resistors first. They're often found in power supplies. Like you can see R34 here is 100 ohms, 7 watts. It'll surely be a block type wire wound resistor. Here's 270 ohm, 2 watts. It'll surely also need to be a modern, updated to a modern wire wound resistor. So those are pretty typical where you will find those big old wire wounds is in the power supply. Very, very common. So now let's talk about the difference that we've discovered between the old-fashioned carbon and the metal film. Being the metal film induce some inductance and where you can and cannot use them. It's really very simple. It's not very hard to understand. But let's look at V1 here. This is an oscillator tube. And this right here now, R number 1, 47K, has got radio frequency directly applied to it. You cannot put an inductive metal film type resistor in there. It's like adding a small inductor here and you're going to change something in that tune circuit that you don't want to change. However, if you look at R2, which is 33K, it's blocked by a capacitor. So R2 could be a standard metal film resistor. So here you would have to put an OY or an OX class type resistor, but here you could use a standard metal film. So if we continue on here now, this R5 is blocked by C5 capacitor. So again, you could put in a metal film. Same here, we're not really dealing with the RF on this section of that tube, and you could put a metal film in. Most of these types of things, there's R6 blocked by a capacitor. But if you go over here to R9, this is kind of sort of the input tune circuit for the 6146 tube. But R9, 1,000 ohms, 2 watts, is not blocked by a resistor at the top of it. This is part of the tuning capacitor. I would not put in a metal film resistor in there. I would want to put in a carbon replacement like an OY or an OX class resistor. This resistor here, this is all audio here. None of this is subject to RF. So all of this can be metal film. Moving over into the power supply, very importantly, probably one of the most important resistors that you use an OY or an OX class resistor is inside the parasitic choke. You often see attached to the top of the power tube, there's a parasitic choke suppressor, and inside the coil, there's usually a resistor. And if it goes, which is not uncommon for it to go, if a tube has a hissy fit or a conniption or burns up or burns down, chances are it will take that resistor with it, and you have to replace it again with an OY or an OX class resistor. So just to keep that in mind. So that's basically how these resistors are used, keeping in mind that if you're going to be putting direct RF through a resistor, exposed RF to a resistor, it really needs to be an OX or OY class resistor. Should not be a metal film. Old-fashioned carbon or OX or OY. So if you have questions about that, feel free to leave them in the comment section below. So there's a little bit of consideration for the types of resistors you use in your radios. And the OX or OY class resistors can be found Mouser. A lot of folks get a lot of specialty parts from Mouser. They're not very hard to find. But I mean, the vast majorities of the resistors you will be replacing in an old radio will be metal film. You just have to be careful to make sure that RF isn't passing through it. The resistor is either controlling radio frequency, or it's controlling voltage, or it's controlling both. You have to make sure that, when you're putting a metal film resistor in, like here now, this is just audio, and to have a little bit of a metal film in here, Here's now a cathode resistor, 33 R23, if you can see that, 3300 ohms. Again, that's okay to put a metal film in, and again, that's a cathode resistor, quite apt to drift because it works hard. So again, like I said, if you have questions, post them below. And I think I'm going to wrap this video up there, and we'll see where we go from here. So thanks for tuning in, and if you're enjoying these series of videos or getting something out of it or learning something, please take a moment and subscribe, support our channel. We'd love it. And I guess that's it, and we'll see you again in the next one.